Hello and welcome back to topic 1B, the kinetic model. Okay, get this loading, get this writing, perfect. All right, so topic 1B is about the kinetic model. Now, as we learned in Gen Chem, right, we learned about the kinetic molecular theory, which is perfectly perfect when it comes to perfect gases. Didn't intend to say it that way, but it's true. Right? In the kinetic molecular theory, perfect gases are in constant random motion, right? Constant motion. They never slow down, they never speed up. They have the same speed all the time, right? Because the volume of gas is much smaller than the container volume, right? The volume of the gas particles are ignored, right? We know that's not going to be true, right? Because every mass takes up volume. And so in these perfect gas situations, we just ignore them. We consider them point charges. That's not true, right? They have actual volume, but that's okay. We'll get there. All right. Intermolecular attractions can be ignored, right? Again, we are totally ignoring any attractive forces, any repulsive forces, and this is not a true thing, right? Under the perfect gas, everything is just flying around like if you had one particle or a billion particles, right? They would be all flying around totally independently of each other. And then importantly, all collisions are elastic, meaning no energy is lost. Again, this is not an accurate depiction of a real gas because any collision, there's going to be some energy lost as heat, as thermal energy, right? Well, we're not going to consider that yet. And finally, the average kinetic energy depends only on the temperature, right? This is, again, not necessarily true. The average kinetic energy can be affected by intermolecular attractions. You know, if two molecules are attracted to each other, they're going to accelerate towards each other, right? But really, for even on this class, we're going to consider just depending on the temperature, right? So if we consider a particle that is bouncing around in a container, right? The pressure of the gas, as it says, arises from impacts with the wall, right? Again, pressure is force over area. Right? We talked about that in part A. Right? Pressure is force over area. And so the force is the literal collision of these molecules, right, as they hit the wall. Now we're only going to look at, and all these molecules are moving in 3 dimensions, but we're going to simplify it a bit and look at only one dimension, in this case, the x dimension, right? So we have one-dimensional velocity here, right? We have a mass moving at one-dimensional velocity, right? If you think back to physics, mass times velocity is momentum, right? So we have this change in momentum where before the collision, we have a mass and a velocity, and it's going in we call it the positive direction towards the wall. But, positive, negative here, just all about direction. Right after collision, because it's going to be elastic, right? If it's going to be elastic, then all of that momentum is going to be conserved. It's just going to change direction, right? It's going to be conserved. It's still m times vx, but now it's going to be a different direction, which is why we go from positive to negative. All right, this is why we go from positive to negative. So if we wanted to show how this affects everything, right? If we think about a box that had a certain cross-sectional area like this. Let's say we have a box like this, right? And we have a particle in the middle of that box. Right? That particle, if it hits this wall, will exert some pressure, right, over the area of the wall, right? This wall has a total area of A, right? And the chances of it hitting its wall, the conditions needed for it to hit the wall is that it needs to travel that distance, right? It's got to travel whatever distance to the wall, right? It's got to do that in a certain amount of time, and it's got to travel a certain distance. Well, in this case, the distance traveled is going to be the velocity times the time elapsed, right? So in any given amount of time, it has to travel a certain amount of distance to hit the wall, right? If the particle is beyond that distance, and it's not going to hit that wall in that particular amount of time. Right? So that's for one single particle, right? But in our gases, we're not going to have one single particle. We're going to have a lot more particles, right? So we're going to have basically like our number of moles, basically. It's going to be the number of particles, or sorry, backwards. Right? This is the number of particles. That's going to be moles times Avogadro's number, right? That gets you the number of particles that would be moving. That could be in this space, right? So we have a portion, we have the total portion here, all the molecules that are in that space, right? And then we have to distribute them three-dimensionally, right? Because they're not all on the same point, right? It's not like they're all clumped up together. They're distributed three-dimensionally, right? Because they're all in a certain volume of V. Right? They're all in a certain volume of V. Right? So only if we put them all together, basically, right, if we put them all together, right, we have a certain number of molecules, right, a number of molecules, right, that have to hit an area A, right? As the area increases, the number of collisions should increase, right? If they travel a certain distance, right? Vx delta t. Right? And then all of these are going to be spread out in a volume. Right? All these are going to be spread out in a volume. And it's going to be, there's a 2 in here from just something else a little skipped, right? So this is what I've written right here is the proportion, the conditions basically a particle has to fulfill in order to make a collision, right? And when a collision does happen, right, the change in momentum is going to be 2 times mvx, right? If we go back, right, if we go from positive mvx to negative mvx, well, the difference is going to be 2 mvx, right? This is where we're getting our change in momentum, wrong one, right? So, oh, I remember now. 2 MBX. So just to mention this 2, where it comes from, like for all these particles at any given time, half of them are going to be moving towards the wall and half of them are going to be moving away from the wall. Like some of them are going to have positive MX and some of them are going to have negative MX, basically. And so this is basically 1/2 multiplied by everything. Right? So again, this part right here is the proportion, right, hitting the wall, right? And this proportion right here is the momentum change, right? Momentum is P. It's kind of annoying because momentum is P and also pressure is P, right? Really kind of annoying, but hey, we have physicists and chemists working kind of against each other. All right. And then if you were to distribute all of this right here, right, you would see that we basically are going to combine in and in A and the mass into one bigger number. All right, we'll call this M. Right, again, M is going to be mass times Avogadro's number. Right, And then we'll have a Vx, right? If we do it, this Vx will be multiplied by that Vx squared times delta T, right? And on the bottom, we'll have one single V because this 2 cancels out the 1/2, basically, right? Now, if we were to calculate, this is the amount of momentum change, basically, right? If we wanted to calculate the force of the momentum change, right? The force of the momentum change is just going to be that section right there, right? So our force would be here N M A Vx squared over V, over volume, right? Because the force, as it says, the rate of change of momentum, the change of momentum divided by the interval delta T, which occurs, is this. And according to Newton's second law of motion, the rate of change of momentum is equal to the force, right? So this is going to be equal to our force. And again, our pressure is going to be force per area, right? Force per area. And so if we were to divide this by area, then our pressure, like the area, would cancel out top and bottom. And our pressure would be Nm Vx squared over V. Right? Now, we're not going to assume that every single particle has the same exact velocity. That would be silly, right? That's not how velocities work. That's not how molecules move, right? There's a distribution of velocities, right? And so what we'll do instead is that we are going to modify this basically. We're going to say multiplying the distribution of our velocities. That's all we're doing. We're just saying we're changing this to the average basically of the quantity, the average of the distribution. Right. Now we'll get into root mean squared speed in just a minute, right? But basically the root mean squared speed, right? Root mean squared is just the square root of the average squared velocity, basically the square root of what we just kind of figured out. And that's root mean squared. It's kind of complicated, but that's just what it is. All right. Now, when we put these together, kind of even things out, and if we include all of the other velocities, if we include the other velocities, then we get this equation here. Like, how do we get this? Or basically, we're assuming here that Vx is going to be, let's put it this way, that our total velocity is going to be the sum of Vx and Vy and Vz, right? The sum of all these things. Right. So where we're basically, it's going to be, right, 1/3 of this, 1/3 Vy, 1/3 of Vz, right? And if we do the root mean squared speed of each one of these particular ones, is just, 1/3 V RMS of X, 1/3 V RMS of Y, 1/3 V RMS of Z, right? We put them all together, and that's how we get just one single V RMS, right? For the entire translational movement. Right? And then all these 1/3 kind of come out together over here, right? You'll notice that we've moved the V over, makes it look a little bit nicer, right? But that's where we get, right? This is the relationship between pressure and volume, right? We have, look at it, moles, easy to do. This is all going to be a constant because it's mass times Avogadro's number. And then the root mean squared speed squared, right? Kind of a weird way of saying it, right? But for any given gas and any given temperature, right, the VRMS is going to be the average based on the temperature, basically, right? We said that, right? The average kinetic energy, we're going to assume, only depends on the temperature. So that's going to be constant at any given temperature, right? The the mass, again, that's going to be a constant. Moles is going to be a constant, basically. And so in this case, we see P times V is going to be a constant in any given system, right? Any given system. Now, this leads into a little bit the Maxwell-Boltzmann distribution. I'll be 100% honest here. Uh, this is a little bit too statistical to me, right? To be completely honest, right? It's useful, but it's also very statistical, right? As it says, in any sample of gas will be a distribution of speeds amongst all the different particles. This is described by the Maxwell-Boltzmann distribution function, right? You can look look it up in the book, right? But this is a distribution of speeds at different temperatures, basically, right? And if you do this, put it all together, right? If you look at the derivation, it's quite long, kind of complicated, right? Not very fun. What you see is that the distribution is a function of velocity, right? Where we have 4 pi times m square root, or m over 2 pi RT to the 3/2 power. It's getting kind of confusing, right? Velocity squared times e to the negative mv squared over 2 RT, right? Lots of stuff going on here. Now, I'm not going to make you use this equation because I think it's kind of annoying, right? Really annoying. And a lot of the questions that are in the book using this equation require mathematical software like MATLAB or stuff like that. Honestly, I don't know how to use MATLAB, so I'm not going to make you use it. We're going to keep it a little bit simpler than that. But we can take some lessons from it. All right. When our velocity is very large, right, then we're going to have the function is going to be smaller. Right. When our velocity is very large, our function is going to be smaller. Press the wrong button there. Right. And so basically what it's saying is that if we were shooting for high velocities, we would expect to find a low probability of that, right? A lower probability of high velocities, which makes sense, right? Our distribution, if you looked at different graphs, are often like things, something like this, right? The extremes of high and low velocity should be smaller, right? When t is large here, right? Our t is on the bottom of this. It's in the bottom of our exponent here, right? Well, when t becomes large, the function gets bigger, right? The function gets bigger means we're going to have a higher chance for higher speeds. Again, if we have, ideally, if we had 0 degrees Kelvin, right? Every single thing would have a speed of 0, right? Everything would be all stacked on top of each other at 0 speed, right? As we increase temperature, we change the shapes of our distributions, right? And we get wider and wider distributions, achieving higher and higher speeds, right? And this goes very easily, right? If we increase the temperature, we would expect there to be an increased average kinetic energy, right? But also increased distribution, right? When our molar mass is large, right, this m molar mass, right, this is on the top, this is on the top, right? And this is all negative, just to keep in mind. The exponent here is negative, makes a big difference. Then our function is going to get smaller, right? So again, if our molar mass is large, if our molecule is heavier, then we should have a lower chance for high speed, which makes perfect sense, right? If our kinetic energy is 1/2, small m, mv squared, right? If the kinetic energy is tied directly to the temperature, right? This is basically going to be constant, if you want to call it. Then as we increase the mass, the velocity should decrease. Right? If we look right here in the middle, in the purple section, right, when v approaches 0, the function approaches 0 too. Right? Well, basically what it's saying is that there's going to be very low chances for very low speeds, right? Same thing with our distribution, right? The very highs are going to be not that common at all, and the very lows are going to be not that common at all, right? Unless we get our temperature very, very, very low, right? And then this red portion here in the middle, right, totally from the book, That's simply to ensure that the entire distribution adds up to 1, right? Because the distribution here is just the probability of finding a particle at any given speed for any given temperature, right? We have speed and temperature. So at any given temperature, what's the probability of finding a particle at this speed? That's the whole point of the distribution. Well, the entire distribution has to add up to 1 because that would be 100% of all the particles. Right. Now, this is mostly what I want to talk about in this section. Again, we're not going to use this all too much because it's just a lot and it requires a lot of mathematical software and all these other things. And I'm not ready to teach that, to be completely honest, but we'll keep it there. Right. Now, if we integrate these functions over a range of 0 to infinity, right, all of the possible different types of, 0 to infinity would be the all possible values of velocity, right? All the different values of speed, 0 being the lowest, infinity being the highest, right? We're not going to talk about negatives and positives in terms of direction, but just in terms of the magnitude, all right? Well, what do we get from these? We'll get several different results, right? If we wanted to look at the mean square speed, right? So again, these little brackets are mean, right? And then we have squared. Well, the mean square speed would be equal to 3RT over M, right? 3RT over M, right? So again, this is R constant, T temperature, M molar mass, right? 3RT over M. Makes it fairly easy to figure out, right? And then the root mean squared speed, RMS speed, would just be the square root of the mean square speed, right? Root of the mean squared speed. Just take the square root of it, square root of 3RT over M, right? And if we were to substitute this equation for any instance of VRMS, we can get backwards, sort of backwards. I don't know if you call it backwards, but we could get PV equals nRT out of it, kind of working backwards. All right. If you look over here on the right-hand side, this is just a better drawing of what I was trying to do before, right? The distribution function, the values of it, the different speeds, right? At low temperature, we have a smaller distribution. At high temperature, we have a larger distribution, right? And at each temperature, we'll have different average speeds, right? The average is going to be right in the middle of the distribution. As it says, the most probable speed, which is typically the average speed, increases with temperature and with decreasing molar mass. And this distribution becomes broader. So kind of what I was drawing before, but better. Right? So leave it to me to, do something bad and then find a better version of it on the right in the exact next slide. Right? Excuse me. Now, from here, we can also do other variations of our speed. Some of them are going to be more useful than others. Right? So if you look on the picture, the side here, right? We have says a summary of the conclusions that can be deduced from the Maxwell distribution for molecules of a molar mass M at a temperature T. All right. First, we have MP, which is the most probable speed. Not exactly the same thing as the average speed, but fairly close, right? So our most probable speed is going to be, right, the square root of 2RT over M. Right, square root of 2RT over M. Slightly different. Right. If we look at next, the mean speed, right, slightly different. This is the true average, right, slightly different than the most probable one, right, because the shape of the distribution, right, the average, since this is basically, this stuff that's shifting the average over from the most probable, right? Our mean speed is going to be square root of 8RT over pi m, right? Which is slightly different again from the root mean squared speed. See, the root mean squared is shifted even more, right? That was our square root of 3RT over m, right? And then also one of the ones that's going to be important when we get into the next section about collisions is the relative velocity, right? So relative velocity is going to be slightly different, right? This is talking about particles relative to each other, right? So if we have two particles coming at each other, right, then their relative velocity is going to be a product of how fast they are coming at each other, right? It's not going to, it depends on exactly what direction they're going. You know, if they're going away from each other, then they have very different relative velocities than if they're going towards each other, right? If we were to take the mean velocity of the entire distribution, you know, doesn't matter what direction they're going. Well, the relative average, when you call it relative velocity, is the square root of the mean velocity, right? We'll use that in just a second or two. Right? So if we wanted to compare the root mean squared, mean, and most probable speed of H2 molecules at 20 degrees Celsius, right? How we can do this, right? Well, our molecular mass is going to be, right, our molar mass, typically we would call this 2 grams per mole, right? And when we get into the formulas, we'll have to change that a little bit, right? And then 20 degrees Celsius, we never want Celsius really, right? We're gonna add 273.15 Kelvin to get the correct answer there. All right, now let's look back. We want to do the root mean squared velocity. So VRMS. Let's look back and see what that was, right? Our root mean squared velocity was square root of 3RT over m, right? So we have the square root of 3RT over m, the molar mass. All right. Now, well, let's figure this out. All right, so we have the square root of 3. All right, R in this place is going to be 8.314 joules per mole Kelvin. All right. And our temperature in Kelvin is going to be 293.15. Right. And then on the bottom, here's one thing we need to be tricky about, right? Compared to when we did root mean squared specifically in Gen Chem, is that our mass on the bottom, because we're using this value of R, needs to be in kilograms per mole, not grams per mole, because grams is not an SI unit, right? It's not a base unit. It's got to be in kilograms per mole, right? Slightly different. All right. So instead of being 2 grams per mole, it's going to be 0.002 kilograms, right, per mole. It's very, very slightly different. Right. And if we wanted to solve that, work out the old calculator. Let's see, the top is 3 times 8.314 times 293.15. I divide that by 0.002 and then take the square root. That answer to get us a root mean squared velocity of 1.912 times 10 to the third, in this case, meters per second. All right, it's going to have to be meters per second. All right, and again, just to point this out here, you say, where meters come from, it's all stuffed into joules, right? A joule is a kilogram meters per second squared, right? So it's all stuffed into joules. That's how we get meters per second out of this. And this is why we need kilograms instead of grams, right? Otherwise, we'd end up with like a completely different exponent, basically. It'd be 10 to the positive 6, I think, would be a different version of it. Right. Now, if we wanted to do the mean, right, let's go back and look at that. Mean is square root of 8RT over pi m. Square root of 8RT over pi times m. All right, well, just more straight up math. We got 8 times 8.314 times 293.15 over pi times 0.002. Right, same difference. I'm going to put this over here. We have more room. Well, let's do that. 8 times 8.314. 8 times 8.314 times 293.15. Right, divided by 0.002 times pi. I gotta find pi on my calculator. There it is. Right. And if I do the square root of that answer, I get, right, 1.762 times 10 to the negative, or 10 to the, sorry, positive third meters per second. Right. 1.762 times 10 to the positive third meters per second. Right. And finally, if I want to do the most probable speed, right, what is that? Most probable speed is square root of 2RT over m. Went too far. Square root of 2RT over m. Right, easy enough. 2 times 8.314 times 293.15 over 0.002. Let's do that a little bit. 2 times 8.314 times 293.15, right, divided by 0.002. Square root, that answer gets me 1.561 times 10 to the third meters per second. Right. Now, one thing you should notice, if we look at all of these different answers, and so they're all very, very close together, right? They're all in the same order of magnitude, 10 to the third, right? It's just 1 point different decimal for each one of them, right? And they should end up being very close, right? If you think back to this graph here, right? These are all going to be fairly close to each other, right? They're all going to be fairly close to each other. If we looked at this actually, right? Well, we can't really tell exactly what the value of each one is going to be because they're on different parts of the curve here, right? We may be tempted to think that because this is at the top of the curve, it's going to be the highest value, but that's not true really at all, right? That's not true at all because the top of the curve is the probability of it being there, right? Not the actual value of it, right? But if you look here, right, what is highest velocity? RMS, then mean, then most probable, which is exactly what we see here on this graph, right? The RMS being the highest velocity, then the mean, then the most probable. So some simple calculations, assuming you know these different versions of the speed. All right. Now, if we want to look at collisions, going from here, because our kinetic model is all about collisions, right? Okay, we have to think about collisions between the particles or a wall, or between two particles, right? So the frequency of our collisions, z, is going to be related both to the size of the particle and the speed, right? If we're talking about two different particles, the size of the particles matters a lot, right? So if we have a particle that has a diameter d, All right, diameter D, right? It's going to have a kind of collision cross section, right? A collision cross section. This is what this is. This is so our sigma here is our collision cross section, right? This is basically how, like, if anything gets within this diameter here, right, this diameter here, then it's going to interact with our particle, right? It doesn't have to hit, it doesn't necessarily have to hit straight on, but it's going to hit somewhere in that area, right? Then it's going to collide, right? And so this particle is going to travel some distance, right? In this case, v delta t, right? And this is the relative velocity, right? Because the relative velocity is for two things that are moving, right? Two things that are moving. And if we're basically going to figure out how often we would expect to see a hit versus a miss, right? So we're seeing, right, this area, which is pi times d squared, right? Or if you think about this, so this right here is, even though it's listed as d, this is basically the radius of the cross-section circle, right? So this is just pi r squared, but instead of calling it r, we're calling it d, which is the collision diameter, the collision diameter, basically, right? And we're moving this circle throughout space to make a column, right? It's going to make a column, right? And so our compression factor, we're going to be moving this cross section, right, through space, right? Right. So we're moving the cross section through space, and then the amount of other particles that are going to be in the way is going to be related to partly the pressure. Right? This is pressure, right? Because if we have higher pressure, then we're going to have more particles in the way. Right? More particles in the way. Excuse me. And this is Boltzmann constant, which I will list in just a minute. And then the temperature, right? The temperature of everything kind of come together. Right? Wanted to make this a little bit more specific. Like basically this section comes from manipulating the ideal gas law in order to solve for the number of particles that are in the way, right? That's kind of where it's coming from, right? So again, our total collision frequency, cross section times the relative velocity times pressure over k times d. K is the Boltzmann constant, right? Not some other k, any other k that we've learned anywhere else, right? This is the only little version we're going to use. Right? So if we looked at this, right, we said the best laboratory vacuum pumps can generate a vacuum of 1 nanotorr, and that's 1 times 10 to the negative 9th torr. We say at 25 degrees Celsius, assuming that air consists of only N2 molecules, right, with a collision diameter of 395 picometers, right? So our diameter is 395 times 10 to the negative 12 meters. Calculate at this pressure, right? This is our pressure here in torr, the mean speed, the mean free path, and the collision frequency. All right. So we're looking at these different pressures, all these different things. One thing we should do, right, because our torr is not necessarily the greatest unit, right? We talked about that. The SI unit is going to be the Pascal. So let's change this to the Pascal because that's going to be better for us. All right, so we have 1 times 10 to the negative 10th torr. All right. And if we go back and look in our book, let's see. There's, where'd it go? there is 760 torr in 101,325 pascals. All right, we're going to change that to a different unit of pressure. All right, let's see what that is. 1e negative 9 times 101,325 divided by 760 gets me 1.33 times 10 to the negative 7th pascals. Okay. So change it to an SI unit, basically. That should make things easier. 25 degrees Celsius, of course, always needs to be in Kelvin. It's going to be 298.15 Kelvin. All right. And we have the diameter in SI units. Everything looks good. So let's do the mean speed, right? Mean speed. Well, we just did that. We look back, and going backwards, there we go. Right, our mean speed was square root 8RT over pi m. Easy enough. There we go. Square root 8RT over pi m. Oh, easy enough, right? So we have the square root of 8. R is still 8.314. Right? Our temperature is going to be 298.15 Kelvin. And our pi and m here is going to be for N2. Right, N2 is 14 grams per mole, which is 0.014 kilograms per mole. Oh, sorry. N2, almost got it wrong, is going to be 28 grams per mole. So our kilograms will be 0.028 kilograms per mole. Right. So 0.028. We do that bit of math, calculate. 8 times 8.314. Right. 8 times 8.314 times 298.15. All right. Divided by pi times 0.028 gets me an answer of 2.25 times 10 to the 5th meters per second, right? Which is very reasonable, right? Because this is the particles flying around, they're going to be pretty fast, right? And then we get to the mean free path, which I accidentally skipped, right? But our mean free path, we go back one slide, there we go. The mean free path is the average distance a particle can travel between collisions, right? Free path meaning nothing's hitting it, right? This is simply the quotient of the relative velocity. So the relative velocity and the collision frequency, that's going to be our mean free path, right? And this mean free path is going to be in meters, right? Because we're literally talking about a distance, right? So the relative velocity divided by the collision frequency. So let's go back. All right. So if we want to do the mean free path, where it's going to be hard to do that right now, right? Isn't it? Because we don't know the relative velocity. Right? We don't know the collision frequency yet. So let's skip that for now. Let's do the collision frequency. All right, our collision frequency was sigma times the relative velocity times the pressure over kT. All right. Well, we have to do a little sub math here, right? Our collision frequency was pi times d squared. In this case, d is going to be 309 or 95 times 10 to the negative 12th squared, right? That's the cross section, right? Our relative velocity, we go back and look. Right? Relative velocity is the square root of 2 times the mean velocity. Right? right? So it's going to be the square root of 2 times, in this case, we know the mean velocity, which is 2.25 times 10 to the 5th. And then the pressure we figured out is, right, 1.33 times 10 to the negative 7th pascals. Right, 1.33 times 10 to the negative 7th pascals. Right. Again, SI units. It's all SI units. That's important, especially when we're using constants like Boltzmann constants, right? We want to make sure we're using SI units because the constants are almost always, not always, but almost always given in SI units, right? And so big, hairy top, right on bottom, the Boltzmann constant, look it up, 1.380, 1.380 times 10 to the negative 23rd joule per Kelvin, right? So this particular constant, joule per Kelvin, right? And then temperature here is going to be 298.15 Kelvin. All right, big hairy mess here, right? If we do all of these calculations, put them into our calculator correctly, it's gonna be the hard part. Right, we do parentheses, pi times other parentheses 395 that's right, 395 negative 12 squared in parentheses times square root of 2 times 2.25 E5 times 1.33 E7, right? The entire top turns out to be 1.0372 times 10 to the negative 6. Okay. All right. Which sounds about right. Oh, wait a minute. I messed up a little bit. Let me redo this. I accidentally put in a division when I need multiplication. All right, let's do this again. Boop. There we go. 2.07 times 10 to the negative 6. Okay. 2.07 times 10 to the negative 6. Right, and that looks reasonable enough. All right, times that. Checking the work. Oh, wait a minute. Here's the problem. Again, I messed up. Variant E negative 7. Let's do this again. There we go. That makes more sense. Top is 2.07 times 10 to the negative 20th. Right, that makes sense. Because if this is negative 24 up here, right, negative 24 plus positive 5 plus negative 7 should end up with a very negative number. Right, in this case, negative 20th. All right, so we do all of that divided by 1.380 E negative 23 times 298.15. Right. If we do that, we get an answer, a path of 5.041. In this case, this is collision frequency. So 5.01 basically collisions per second. Right. It's a frequency, so it's per second. Right. If we wanted to do our backwards to our mean free path, right? Again, this is relative velocity over the collision frequency, or our relative velocity we figured out was square root of 2 times 2.25 10 to the positive 5th, right? Square root of 2 times our mean velocity, right? Divided by our new collision frequency, 5.041. Right. Well, if we do that, what is it going to be? Right, it's going to be the square root of 2 times 2.25 10 to the 5th. Oh, I got a square root of 2 times 2.25 10 to the 5th, right? And then divided by 5.041, which is going to be 6.31 times 10 to the 4th, right? Meters. 6.31 times 10 to the 4th meters. Right. So we have 3 different answers here. Now, let's use a little bit of math sense, make sure everything makes sense here, right? 2.25 times 10 to the 5th meters per second. That's pretty fast. Well, molecules are very small, so they move very fast, right? Collisions per second, 5. It's hard a number to figure out, honestly. But the mean free path of 6.31 times 10 to the 4th meters, that may seem a little weird, right? Right? You think, well, that's a pretty big number. That's a pretty big number, right? But one thing you have to consider is that this is at a very low pressure, right? This is like the pressure of outer space, basically, right? And if you put a particle in outer space, you would not be surprised if it went 63 kilometers before it hits another particle, right? That would not be surprising, again, because the pressure is so very, very low. It's not a surprise there. All right. Anyways, that'll wrap up all of topic 1B. And we'll pick up topic 1C, real gases, on the next recording.